Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Caprice Phillips with us today. Hi,
Hi.
Caprice.
Hi, thank you for having me.
Oh, well, thank you so much. It's a really great article, and so I'm really glad you're going to be able to walk us through it. What's your geolocation? Where are you at?
So right now, I'm a graduate student at OSU, so I'm in Columbus, Ohio right now.
Mhm.
Yeah,
And is it turning fall?
it is. Well, the tree outside of my window is turning very fall-esque. They're starting to fall and change colors. It's a bit warmer today, which is a little disappointing, but it's gonna. I can't expect to be falling. Boom! It's like 67 degrees, but that's not how
Yeah,
Mother.
just to date this video, so we just went through equinox the other day.
Yeah, so but cooler weather is coming. I can see it in the forecast, so that's something to look forward to. So.
I think here in Phoenix, we probably have a little ways before we cool off a little bit.
Oh
We're
yeah.
down a little bit, but we're still in the pushing up into the 108 Fs, 40 F kind of thing, 40 C.
Yeah,
Excuse me. Um,
I don't envy you.
mm,
It's hot.
I like it. I like it. I do not mind the heat at all. That is a pretty awesome shirt there. It's got all kinds of squiggly symbols and equations on it. Very cool.
Oh, thank you. Thank you. Hidden Figures.
Yeah, very good. You got that at the double S?
I did. It was a few, what is this? 2020. Time isn't real anymore, but
Yeah.
2020, I think maybe it was 2 or 3 years ago. I think I got it from Star Tourist. I
What,
think
what what city was it in? Did you go to?
it was in Maryland.
Mm-hmm.
The I think it was like the last one they had, like the contract for the hotel or something like
Yeah,
that.
yeah. Mm-hmm.
Yeah, it was great crab cakes and great conference. So
Yeah, the crab cakes were good. I got
yeah,
it.
great shirts.
So how are things at Ohio? Is are classes in session, or are people is the university generally operating, or?
Yeah, so I guess we're doing what they say is like hybrid model. So some classes that you either can't avoid or the teacher have chosen to like have them like hybrid, like they're doing kind of that. Like I'm kind of all online because I did not want to go to campus,
Yeah.
but the faculty and like the department has been like really supportive of like my decision to do that. So but anything need from me they can get from Zoom, so it's been fine so far.
Well, you must be like ABD, right? All but dissertation.
Oh, actually, no. Like, I'm only a second year at.
Wow.
Yeah, I'm only fingers crossed. Foreseeing the future. I'm just a PhD student right now, not a candidate yet, but probably the next year or so,
Mm-hmm.
I'll start on like my candidacy here at like OSU. So
Very cool. So that's pretty awesome. You got a first author paper out before your qualifiers. That's pretty good. So what do you like to do in general for research, Caprice?
So in general for research, I'm really interested in brown dwarfs and exoplanets, like substellar objects, like in general, is kind of something that really fascinates me. So yeah.
Awesome. And that is going to lead us into this really lovely article. 2MASS J, very long telephone number. A young companion at the substellar boundary with potential membership in the β-Pic moving group. And Caprice, take us away.
Okay, thank you. So before I start, just a little kind of background and motivation for this project. So my advisor at the time, the second author, was very interested in this object here and the Beta Pictoris moving group. So they kind of noticed this object, 2MASS, very long telephone number, 2MASS in the literature, but they noticed that it seemed to have been kind of overlooked a little bit, like not much mentioned. And so what's interesting about this object is that it seems to be very kind of similar to another brown dwarf companion in this movement group called PZ-tail B.
Okay.
And so it's very like important to find like movement groups are very useful because we know their age, they're all formed together. And so age is something that's really hard to kind of constrain down in astronomy. So if you have objects and, that you can age date them and they all form together, it makes it a lot easier. And so, understanding brown dwarfs can help us like understand more about different formations and different things about exoplanets, because brown dwarfs are easier, to study than exoplanets are. And so what's interesting about this object as well is that, it was similar to another brown dwarf in this moving group, is that it's really far away, unlike PZTL b, which I can't remember the exact number, but it's closer to its host star. So this one's far away, so it's not lost as much as in the glare of the host star. So it makes it easier to study things like in its atmosphere and characterize it, and different things like that. So that's kind of like some background and motivation for this project.
Cool. All right. Should we take a look at figure 1?
Yeah, we can go ahead. And I just kind of did a little introduction.
Intros. That's why we start out papers with intros and abstracts. So,
Yeah.
The goal. Okay, figure 1. Let me blow that up for folks. And, oops, got to make sure that's on. There we go. Sorry about that, everyone. Okay, so what do we got? We have.
All right. So this is a spectrum of the object here, the companion. So we have like a few different kind of data for. We have some near infrared H and K from IGRN. So we also have a near infrared JH and K band for the companion from the SPECS instrument on the IRTF telescope. So what it's showing here is kind of the different J, H, and K bands with just some markers where some like characteristic things for some later type M dwarfs are, like potassium, titanium oxide, and different things like that. And there's a CO band around like 2.25 like microns there. So that's just kind of showing that the spectrum that we use for a lot of the data analysis. This is just a visualization of that, so viewers can see like what some markers are inside of it. So.
And there's some gaps in this spectrum. Were those removed?
Yeah, so that's just kind of like where some water bands are. We just like the low signal to noise region.
Okay.
Yeah.
Okay, very cool.
Yeah.
Okay, so there's our spectra.
Yeah, and then we just talk about some things about observations and different things, like have some direct imaging as well, which kind of brings us into the next figure. Yeah, so another cool thing about this project, actually, they already had adaptive like AO image, adaptive optics image of the system, but I got to go with my past advisor, and we got to go out to, they had some telescope time at Keck, and so I got to go out with them. It was my first time in Hawaii, which was super exciting. I got to go out with them, and we were able to get another image of the system in the H band. So what you see here is on the right is the host star, which is like an M2, the A component there, and then the B really far away. It's like separated by like 650 AU is the companion that I was studying for this project. And speaking of
what is the rough distance?
The distance away, it's like around 70 parsecs away. Yeah.
Okay.
And so kind of speaking of host stars, over here on the right is just it's an optical spectrum of the host stars, showing that there's some lithium absorption and also some H alpha emission, kind of one of the things to show that the system, to age date the system, that it is like young. So that was one of the things, like later on we just dropped in the paper to kind of show different markers in the host star.
And that's based on the lithium abundance, yeah?
Yes.
Yeah. Okay, I'm good.
Yeah.
All right, and we got.
So just scrolling down just a little bit like more about our project. So when we first started off, like the first steps were to classify the system, like get things like spectral type, and we found like an M6 you know, ±1 kind of spectral type. We kind of started off doing like little check markers for if it was similar to PCTLB,
Mm-hmm.
the other companion to kind of compare the two. So like, you know, what's the spectral type of this object? We're like, okay, it's similar to PCTLB. They're both around M6. And then also another thing you want to find out is, you know, what's the surface gravity of this object. There are certain markers, and then there's some on the next page, a figure on the next page, the one on the right. So there are certain markers in the near infrared that are affected by surface gravity. So, you know, the shallower the kind of absorption feature, you know, that will mean that it has a lower surface gravity. So here you see in figure 6, the very colorful one at the top right, sorry, the very colorful one at the top right. Oh, sorry.
I'm
Yeah.
sorry, my bad.
No, you're fine. I know they're all very colorful. The very colorful one, you can see like in the green is a similar spectral type object. That's like something called like a field object, which is a lot older than this one. So, and the one in blue is my object that we study. You can see that some of the features like in the near infrared are the absorption features are not as deep, which is, like I said, a sign that it's young. So it's another thing, like we also part of the study wanted to do like different things to kind of confirm that it is young, like based on some kind of discrepancies and stuff like we saw in like some of the like analysis. So it's just another example of us doing that.
Okay.
Yeah.
Nice. That's true.
And the other figures are not as crucial. It's just like spectral type information. But what was interesting when we looked into things to fit different databases of spectral types, we noticed that the spectrum fit pretty well to the best fit one was to an M6, and it was a younger, like a very low gravity one. But we also noticed that just like visually, it also seems to fit well to and filled M7, which was very strange because you're like, oh, you know, it's in the beta-Pic moving group. It's supposed to be young because beta-Pic is like 23 million years old, but it fits to this field object, which we're like, okay, we're starting to get a little weird here. So that kind of started shaping the project a little differently and stuff. Yeah.
Okay.
Mm-hmm. So we also did some atmospheric characterization to get things about its surface gravity and like effective temperature. And once we did that, like we saw that, about 2800 Kelvin, I think PCLB is around 26 to 2700 Kelvin, and they both have like low surface gravity. So we're like, okay, another check mark, they're both similar. You know, that's something we can like, you know, do a happy check mark for as well. Still trying to compare those two different objects because, you know, they're thought to be the same. Yeah. So we did that, and then let's see, it's just a table, and these are just some chi-square plots showing the best fit for different things, describing what I was.
Yep, that's the minimization process.
And so now this is kind of where the project starts getting a little wonky, is the things with its bolometric luminosity. So for those, like, if you aren't familiar, so if you have an age, and that's why finding groups in the beta in like moving groups is so important, because you know the age and luminosity, you can use like substellar evolution plots, and you can figure out how massive something is. And it's important to know the mass, because mass is what separates a brown dwarf from like an exoplanet or a low mass star. So we got out this luminosity value. And so if we move on to the next page, like the next thing was like, okay, we supposedly know the age. The next thing is to figure out the mass. So I actually think the plot is like further down on a different plot. It's kind of like arranged kind of wonky.
Yeah, I was just doing a quick scan for the number of mass, radius, so you're going to get it all here.
Yeah.
Space velocities.
Yeah, space. Sorry, I think it's on the next page. It's kind of like
all good. Table, and then we got chi-square for different known groups.
Chi-square plots.
And then the chi-square using a different one, velocity.
Yeah. Oh my God, it's on the last start.
And then CMDs.
Yeah.
Numbers. Okay, well, here we go. This is age and mass and luminosity.
Yes, here we go. So this part I think is one of the more kind of crucial plots for the paper. So before I mentioned, you need luminosity and age to infer mass from these evolutionary plots. So what we have here in the orange line are the evolutionary plots of brown dwarfs, and then in the blue is the evolutionary plot for low mass stars. So when we take the luminosity that we got and we plot it on here, we get out a mass that's like 99 Jupiter masses, and the cutoff for brown dwarf is around 75, or some people quote 78 or even 80. So it's like way above. It puts it in the low mass star range, and we're like, wait a minute, this is kind of weird. Like, we thought this object was a brown dwarf, and from the plot and other things we found, that doesn't seem to be the case, because if you look, these are different markers for some substellar objects in the beta-Pic moving group. So they all seem to follow this natural progression, M6, M7, M8, they're all, these spectral types in this moving group, they're brown dwarfs. But this one that's an M6 and has similar characteristics to PCTL B, this little, that I think it's brown star, that's clearly a brown dwarf, is very different. So that made us kind of like bat an eye. Yeah, right there. And it's like, what's going on here? So this is where I mentioned before, where we start to question things like, what's the radius look like? How big is the radius? Is it more inflated? That's showing that it's younger. Like, we start looking for different signs of use, and if it even belongs in this moving group. So if you go, yeah, I know, right? So like, it's like, okay, if it isn't, is it even a brown dwarf? Like, does it belong in this moving group? So if you go back to the kind of the UVW, sorry, I think it was a while up.
Okay.
Yeah, so.
Okay, let's go back to UV. Yes, is it actually in beta-Pic? Okay.
Right. Then the next thing was like, is it actually in beta-Pic? And so we actually went through a few different methods to try to determine this. So one of the ways to do that is to look at the UVW, like space velocities and kind of the galactic positions. So here we have some like U versus W and UV and VW. So the one in the dark pink is kind of where I think it's like 3 sigma difference between the center out for the area for the space velocities for the beta-Pic moving group. And so this one, the star and the, I think is it a pentagon? I can't see. The star and the pentagon here are the O star and the substellar companion, and they like don't seem to lie within the boundaries for this moving group. They're all the way down. It seems like they better fit to like another moving group. And so we also use something called Banyan Sigma, which is a moving group analysis tool by, I think, Jonathan Gagne.
Yep.
So what you can do is you can enter things like its RV, its position, and different things like that, and it will tell you the probability that it belongs to a moving group. And so, we input those calculations, and then we got out that it was like 99.9% chance that it belonged to the field and was not a part of any moving group.
Okay.
And then we're still like, okay, like, what's going on? So that's why, if it doesn't belong to the beta-Pic moving group, there's a question of like, how old is it? And so that's why we looked at markers like the lithium in the host star, is the radius inflated or not? Because it's inflated when it's younger, and then eventually, degeneracy, they all will go down to about a radius of like 1 Jupiter radii.
What is the dark triangle?
Oh, sorry, the dark triangle, that's actually, it was a recent paper that Trinh Dupuis had recently discovered, like a binary M6 and M6 brown dwarf in the beta-Pic moving group. So I put that, and as comparison for it as well, to also show that it doesn't lie. It lies sometimes within it, and also it lies outside of it, but they have like confidence that it does belong with it, with the group, like as well, like as comparison. Sorry, it's like in the text, but like the text is long, so sorry I didn't explain that earlier. Did you have any other questions?
So you got space velocities and you got XYZ. So does one conclude this is not a member?
So the thing is, like, we go back and we say that we test out other methods, because the, you know, the bang and sigma, it's like not perfect. Like if it has like a large kind of yeah, large like dispersion, and the space velocities, like that can also be tricky with the calculation. So we try different methods to take into account for that. Those were the chi sigma, the chi-squared, the chi-square plots came into play in the other thing. And so like, even though it seemed to better match the, like the kinematics and the space velocity for other moving groups, when you look at those groups and where they all generally lie in space, they're like too far away. For example, like the distance that it is, that would be like the average, you know, where they lie like 100 parsecs away or something, and this one's like 70 or something, or it'd be too close, and it's like it doesn't match well to like where they are physically, like in space, but it would match to like the space velocities. So we actually come back and say, like, we have like two different things. Like if it does belong to the beta-Pic moving group, then it would maybe be like a kinematic outlier. And if it, you know, another thing, kind of backtracking, another thing we thought that is maybe this is a binary. So there's actually plots to show of some images. I think it's later in the.
Well, I didn't take a peek at those.
Mm-hmm.
Those are going on linear here. Yep, that looks something like this.
Yes, so we reduced the AO images using row subtraction method. So kind of the thing is, like, if there is a companion, that it would be kind of special to just the B component, and you wouldn't see it in an A component. But when we reduce the images, you see there's like a little blob in figure 18, this little blob to the side of it, but you can also see this little blob in both the host star and the companion. So that's just a sign that it's like a speckle as a part of like observation. It's not an actual unique companion to B, because it's in the same position. Yeah, it's in the same spot and area as the
is an A
star. Yeah, so it's like, oh, it's not special. So that was like,
well, okay, then maybe they're both binaries.
yeah. It's like maybe they're both like binaries. Yeah, so that was the thing. Like we tried to rule out like binarity that way, like if it was a visual binary. So the thing is, like, the whole thing about this system is kind of like we're unsure. It's a very like peculiar kind of system. Like we don't know if it's a binary, we just can't resolve down yet. We're not sure if it belongs to the moving group. It seems like once you look at all these different chi-squares for the UVW and the XYZ, you know, things point back to the beta-Pic moving group, but like using a membership tool, it says no. So the thing is, there's just a whole lot of things we're unsure about. But that's
mysteries are good. Mysteries are good.
Yeah, mysteries are good. Like that's when I first started working, I was like, oh no, it's bad. And my brother's like, no, like you said, mysteries are good. Like the fact that like we don't know, and it's open for more research and stuff is what makes it interesting. So that's kind of where we left off. But we did show that there were different indicators that the system was young, with that very low gravity classification, like the inflated radius, and like the lithium and the host stars, where we kind of left off, like for the reader to show that we're unsure, but there are signs of youth. So
very cool. So thank you for sharing that. And where do we go from here, given what you published and given that we have so many mysteries? Are there, I mean, you don't have to spill your PhD project or your next project, but are there other observations coming online that can help resolve some of these mysteries? Are there new telescopes coming online that can resolve some of this, or just sort of look in your crystal ball and, you know, where does this go over the next 5 years?
Yeah, so I think one of the things that will help is like finding new kind of moving groups, because they're with Gaia and stuff, and as we like get more RV measurements and different things to better constrain the members that are in these groups to see if there are other stars that belong to these groups, or other separate entire moving groups that maybe this one can belong to if it doesn't belong to beta-Pic. So like Gaia, and of course everyone's looking forward to like, you know, James Webb to better characterize, you know, atmospheric properties of this, to get better measurements for things like its spectral type and like, you know, all those different kind of components. So I think like those two would be good. I'm actually working like on a different project now, but you know, it'd be great to, you know, one day like follow up on this. I think would be really exciting to kind of try to unravel the mystery of
Exactly.
this object. Yeah.
You know, projects have a way of boomeranging back.
Yeah.
Yeah, you know, I did something on that at one point. I had to get back to that. Yeah.
Yeah.
Great.
Mhm.
Cool. Cool. Very good.
Thank you.
Caprice, thank you so much. And that'll do for this one, everyone. And we will see you on the next one. Thank you. Bye-bye.
Thanks, everyone.